In this video, we're continuing the graphs of polynomials, but focusing on the concept of multiplicity. So first, before we do, we also need to understand these two concepts. So the fundamental theorem of algebra, this tells us that if we have a polynomial, let's say to the nth degree, then it's going to have exactly n zeros. So what we mean by that is, let's say, I've got a polynomial that's, I don't know, like 2x to the fifth minus 4x cubed plus 2x squared minus, I don't know, 7, right? So we've got this graph here, this polynomial. And if I were to graph this function, that's f of x here, what the fundamental theorem of algebra tells us is that if I have this degree of 5, then how many zeros should this graph have? It should have exactly 5 zeros, 5 roots. So remember, zeros are where it's crossing the x-axis. Then the remainder theorem, we've actually talked about this when we were doing our long division and synthetic. So remember that process is, if you recall, that when you divide and it is a factor, only when the remainder had to be what? 0. So this is now the official name. So the remainder theorem is when you divide, you end up with, if you end up with a remainder of 0, then it is a factor. So again, here, this is just P of A is equal to 0, again, showing that the remainder is 0, if and only if it is a factor of our polynomial. So here with the graph and to relate all this, we're going to also now bring in the multiplicity. So multiplicity, what this means is we could technically have a factor not that appear more than just one time. It could happen 2 times, 3 times, 4 times. It could happen more than once. So if you have a factor that appears more than once, we're going to call it a concept of multiplicity. So here, to identify from the graph how many times or what is the multiplicity of that factor. So if we're going to call it a slice, if the graph slices, so like here, for example, at 4, notice how the graph goes shoop and slices right through it at 4. That's when you have a multiplicity of just 1. So it's only just cutting right through at that 0 at 4, meaning it has a multiplicity of 1. So if the root is even, then it's going to do what we call bounce. So it's not going to necessarily cross through it, but it's going to bounce it. So it could be even. So it could be 2, for example, right? So look at -1. Notice how here it's going up and then bounces, right? So it bounces right off that x-axis right here at -1. So this would show here, this example has a multiplicity of 2. Now, if the root is odd, meaning that it has a multiplicity of 3 or more. So it could be 3, it could be 5, right? It could be higher than that. And sorry, let me go back. I know I said 2, but you could have 4, right? And then going on and on. You could call this a bend or I just realized this got cut off, or it could slide, right? So it could bend, it could slide when it has that multiplicity of 3 or more, when it's odd. So it's still technically crossing. It just looks like it's bending or sliding. So like see here at 2, see how the graph is kind of like sliding along here? Now it's still constantly increasing and crossing at 2, but this shows that odd. So in this example, this 2 here has a multiplicity of 3. So in this case, we also, the roots and their multiplicities must add up to the degree. Oh, I just realized I have that already typed here. Sorry about that. Unless there are complex roots. So there could also be not just real, but complex roots. So the roots must always add up to that degree of the polynomial unless there are complex roots. So like in this case, here, this has a degree of 1, 3, 6. So this graph here has a degree of 6. So even there's only 3 roots, it has a degree of 6. So like for this example, and you do have the equation here, so f of x, oh, sorry about that, is equal to negative x cubed plus 3x squared minus 4. So the fundamental theorem tells us that there should be how many roots? Well, 3, because that is the highest degree here. Now let's identify the roots, but also their multiplicity. So I notice we have a root here at -1, and we also have a root here at 2. But now let's identify the multiplicity, because we only notice that there are 2 roots, but fundamental says we should have 3. So notice at -1, what happens? Well, it slices right through it, right? There's no bounce or slide, it just slices. That means it has a multiplicity of 1. So we have a multiplicity of 1 here. Then let's take a look at 2. Well, it doesn't slice, it doesn't slide, it just bounces, right? It never crosses through, it just bounces. And so here, this shows a multiplicity of 2. So that now showing how these 2 roots here, but if you notice their multiplicity, still add up to 1 plus 2, which is 3. So it still adds up to that degree. Now also just to show you guys, multiplicity is also representing the degree. And if you recall, right, the degree is just another word for the exponent. So if I also wanted to write this out, remember here, guys, when we write out our factors, we always, when we had the solution, we had our answer here. But whenever we're writing out in factored form, we always had the change of the sign. So we're not going to put -1. This is representing x plus 1. So we have our function here of +1. Then here we have +2. So when I write this out in factored form, this would be x minus 2. But we have our multiplicity. Multiplicity of 1, well, that's just an exponent of 1. So I'm going to leave that alone here. But notice how we have a multiplicity of 2. So I'm going to show how this should be x minus 2, but raised to the second power because it has a multiplicity of 2. So here again, the reason why we're changing the sign is if you recall when we solved and we said that this was 0 is equal to, let's say, x plus 1 times x minus 2. What would we then do to solve for x? Change the sign. So notice how we're back to that -1 and +2. So that's just that reminder why here this would be the equation in that factored form. So you know what? Let's go ahead and let's prove that, let's say x plus 1 is a factor using synthetic division. Or in this case, remember, right, we're not going to use that +1, our value, we're going to use -1. So I'm going to use -1 and then our equation. So using the coefficients, but notice how we went 3, 2, missing our 1x here, and then to -4. So our coefficients are going to be -1, 3, then 0, and -4. Go ahead and pause the video. Do this on your own, and then let's see. And remember, right, what should happen if x plus 1 or -1 here is a factor? And here we go. So remember with synthetic, bring down. So this is -1. Now multiply always below the line. -1 times -1, +1. Then we always add above the line. 3 plus 1 is 4. Then we start again. -1 times 4, -4. Now add above the line, you get -4. Then multiply, negative times a negative, positive, and add above. Notice what happened? You get that remainder of 0. So that's how we know here that x plus 1 improved, that x plus 1 is a factor. So if we were to do the same thing, but with +2, right, to represent our x minus 2, what should happen? You get a remainder of 0. That's the remainder theorem. So here, looking now at our next equation and the graph. Fundamental theorem tells us that there should be how many roots? 6 roots. Good. Because our highest degree of our graph here, our polynomial, is 6. Now let's identify the characteristics. So here we've got our roots, multiplicity. So here I've got my root at 1. We also have here our root at 3. We also have our root here at 5. Now let's identify though, because there's only 3, but we should have 6 according to this. So now let's check the multiplicity. Well, looking at 1, what happens with the graph? Boop, cuts right through it, right? So that means it has a multiplicity of 1. What happens at 3? Notice how it doesn't cut through or it doesn't slide, it bounces. So bouncing at 3 means it has a multiplicity of 2. Then notice here at 5, what happens? It goes through it, but it bends. It slides at 5. So that means it has a multiplicity of 3. Because notice how? What's 1 plus 2 plus 3? 6. So now if I wanted to write my equation, then that would be, right, x, y, or f of x or y is equal to not x plus 1, but x minus 1 with that exponent multiplicity of 1. Then here we would have not positive 3, but x minus 3, but because it has a multiplicity of 2 to the second power. Then here, not positive 5, but x minus 5. Then notice how with the multiplicity of 3 to the third power. So now here is our degree even or odd. Well, here we have our both ends, right, going in that upward direction, both ends. So this is an even degree here. That means if they're both positive, and according to our equation, our leading coefficient is positive. And let's see if we remember that end behavior. So as x's are approaching positive infinity, so as we're reading our graph to the right here, going to the right towards positive, our graph is going up, y values, up towards positive infinity. So then as the x's are approaching negative infinity, so as we're reading our graph here to the left, so as we're reading it to the left here, our graph is also going up towards positive infinity. The y values are going up towards positive. Go ahead and pause the video, try these characteristics, and let's see what you get. And here we go. So again, looking at the roots and multiplicity, notice how we're here at -4. You also here at -2. And we also have here at 3. So these are our 3 roots here. But now let's see how you did with the multiplicity. Notice how it happens at -4. Shoo, cuts right through it. Multiplicity of 1. -2, what happens? Shoo, cuts right through it. Multiplicity of 1. What happened at 3? It doesn't cut through it, it doesn't bend, it didn't even cross through. It bounces right off, making that here now in this case a multiplicity of 2. So then for those of you who wrote the equation, just to see if you got this with our roots and multiplicity, we have our f of x or y is equal to not x minus 4, but x plus 4 with an exponent of 1. So we're going to leave it as is. Then here, x not minus 2, but plus 2 with an exponent of 1. Then here, not positive 3, but x minus 3. But because it had multiplicity of 2, it has a degree or exponent of 2. Then here, notice how both ends are going in the same direction. So this degree is even, and because they're both going up, the leading coefficient here is positive. Then the end behavior. So again, as we're going towards x values, towards positive infinity, notice here our graph, the end is going up towards positive infinity. So our y values are going up. Then here, as x's are approaching negative infinity, so as we're going to the left, notice here how the graph, our end is going up, again towards positive infinity. So our y values, f of x, are going towards positive infinity. Then we had some practice problems for you in the notes. So there were these two and these two, so same thing. So go ahead, pause the video, Try these practice problems and let's see how you do. And here we go. So here with our roots and multiplicity. So here I'm at -3, 0, and 3. Sorry about that. Then let's check that multiplicity. Cutting through, so multiplicity of 1, but it bounced at 0, so a multiplicity of 2. Then here, cut right through it, multiplicity of 1. So now notice our degree, both ends going in the same direction, so this is even. Also, actually notice, and I didn't realize this, I didn't mention this earlier, what do our degrees add up to? 4. And what is 4? Even. So that's also a way to check to make sure as well. The leading coefficient, well, if both are going in the same direction but towards negative infinity, that means the leading coefficient here in this case is negative. Then that means our end behaviors are going to be the same. So again, here as x's are approaching positive infinity, what direction are y values going? Negative infinity. As x's are approaching negative infinity, so as we're going to the left here, our x values, our graph again is going towards negative infinity, our y values. So then here, for the second one, our roots, the roots here are at -3 and at 1. Now here, multiplicity, notice how it's cutting right through, so multiplicity of 1. But then notice how this bends, it slides at 1. So for this case, this does have a multiplicity of 3. Oh, and I just realized Miss Reiner made a boo-boo. I missed a root. What root did I miss? -2. So -2 here, and again, slicing right through it, has a multiplicity of 1. Then that means here looking at the degree. Well, 1 plus 3 plus 1 is 5. So let's check to make sure that this is odd. Notice how the end 1 is going up towards positive, 1 is going down towards negative. So yes, this is an odd function. Then what's the leading coefficient? Well, if I were to connect them, right, left to right, notice how we're going up. So this is a positive leading coefficient. Now let's check our end behaviors. So as x's are approaching positive infinity, notice how our graph is going up. So the y values are going up towards positive infinity. Then here, our x values are going towards negative. As the x are going towards negative infinity, as we're reading to the left, our graph is going down. So the y values here are going down towards negative infinity. Then I just realized too, but I'll go through with this one. For those who try to write the equation with the roots and multiplicity, y is equal to not x minus 3, but x plus 3. Then here, I've got not -2, but x plus 2. Then not +1, but x minus 1, but with that degree multiplicity of 3 here. So now let's check these last two. The roots. So here, I got at -3, at -2, 0, 2, and 3. So I've got -3, -2, 0, 2, and 3. So now with our multiplicity, I'm noticing actually with all of them, it's a slice, slice, cut through, shoo, cut right through. So that means they all have a multiplicity of 1. That means here, just to check, 1, 2, 3, 4, and 5. So let's check to make sure that we have that degree that is odd. Notice how we have one end going up, one end going down towards negative infinity. So yes, this is an odd. Then here, the leading coefficient. So as I read it left to right, right, and connecting, notice how the graph is going down. So leading coefficient is negative. Now with my end behavior, so as x's are approaching positive infinity, right? Read the graph to the right. Notice how our graph, our y values are going down towards negative infinity. Then here, as x's are approaching negative infinity, so as we're going to the left here, notice how the graph is going up. So our y values are going up towards positive infinity. Then the roots and multiplicity for our last one here. So we've got -3, -2, and 1. So again, -3, -2, and 1. Then notice here again, slice, slice, slice. So that means they all have a multiplicity of 1. So these add up to 3. So let's check to make sure that the degree is odd. I have one end going up, one end going down. So yes, we do have a degree that is odd. So to check the leading coefficient, read it left to right. Notice how going up. So this leading coefficient is positive. Then our end behavior. So as x's are approaching positive infinity, as we're going to the right, our graph going up. So our y values are going up towards positive infinity. Then as the x values are approaching negative infinity, so as we're going to the left here, notice how the graph is going down. So the y values are going down towards negative infinity. So actually I realized too, this one, if you did the equation, y is equal to x plus 3 times x plus 2 times x minus 1, because they all had a multiplicity or exponent degree of 3 here, or degree of 1. So this here is the extension. Now, instead of numbers, it's giving variables, but it's all the same. So let's see what you think here in terms of the equation and focusing on the multiplicity. And here we go. So noticing here, we're trying to figure out going to that equation. So here we have zeros at -c, -b, and +a. But then looking at the multiplicity, I notice at -c, it bounces, right? It didn't cross through. So -c has a multiplicity of 2. Then here at -b, it slices, cuts through, multiplicity of 1. At a, it cuts through, multiplicity of 1. So I know for a fact here that if I've got a multiplicity, right, of 2, I should have a degree or exponent with one of my factors of 2. So I notice only C and D have an exponent to show that multiplicity of 2. So I'm going to cross out A and B for test taking purposes. Then I have to remember when we were writing in our factored form, we're changing the sign because this is our solution. So going back to factored, that's not going to be -c, but +c, x plus c to the second power. Then x plus b and x minus a. So that's why here the answer is D. So why is the answer not C? Because notice the signs stayed with the solution. So in factored form, remember we do need to change that sign.